Okay, let's quickly take a look at histogram equalization. Before that, let's start with contrast stretching that we did. We in fact there discussed that contrast stretching as a part of histogram, but truly if you look at it, there is nothing much to do with histogram as such for contrast stretching, right? What is all the information that you would require for applying contrast stretching? A image is given. You want to apply contrast stretching. So what is the information that you would extract from that image in order to perform contrast stretching?
IMAX, IMIN, and the histograms.
That's all. IMAX, IMIN, and any other thing is required for doing contrast stretching?
The bit size.
Yeah, right. So the maximum, yeah, bit size. That's what you would multiply with. This is all you would require. So although we discussed it as a part of histogram, the histogram, all that we are using it for is where your non-zero bins are starting and where your non-zero bins are ending. That's all what you are looking at when it came to contrast stretching. Let's say you have values now from imin to imax. You want to bring this imin to 0. So from the whole image, you are subtracting imin. So that will make the minimum value to 0. And now after this subtraction, of course, your max value would come to imax minus imin, right? So you divide the whole thing by imax minus imin. So whichever is the maximum value there, that would now go to 1 and then multiply with maximum intensity value that you could have. Okay, that's so our assumption there is that when you say an image is an enhanced image, an image is a good image, there what you mean is you have distributions of intensity spread from minimum intensity to maximum intensity. Now, when it comes to histogram equalization, the way it is looking at it is you order them in increasing or decreasing order of intensities. Let's consider without loss of generality, increasing order of intensities. By the time you reach, let's say 40% of your intensities, okay? So that means your histogram also ideally should be, that intensity should be there somewhere at the 0.4 times the maximum L minus 1 value you could have. That's the basic idea in histogram equalization, where in other words, if you consider the intensities, so number of pixels having a particular intensity is more or less same. That's the basic idea here. Is the derivation also clear for you? What we did in the, what we did there? Hope this derivation part is also clear. Are there any questions as far as the derivation is concerned? Because I'm going to give you something to derive now, if it is clear. Then I assume it's clear. Anyway, it will get clarified if there is also some issue in due course. Okay, so I think if you notice in the in that video, I was putting a couple of questions at the end. One question is your transformation from R to S, okay, is the transformation from R to S, is it monotonically increasing or monotonically, what is the nature of it in terms of increasing, decreasing, monotonic and strictly monotonic?
So it's monotonically increasing.
It is
Yes, sir.
monotonically,
Monotonic.
it is monotonically
increasing.
Good. Is it not strictly monotonically increasing?
No, sir.
No.
Yes.
Can it be sometimes strictly monotonically increasing?
Yes, sir.
When
Yes.
can it be monotonically increasing? Or at least when is it that there is a possibility for, or maybe I think the better way to look at it is why is it not strictly monotonically increasing most of the times?
Because of the rounding up.
Because of the rounding. Okay, let me ignore, I agree with that. But in addition to that, there is some other instance also when you would get it not strictly monotonically increasing.
Sir, but finally it has to saturate at some value, right? So how can it be strictly monotonically increasing?
No. The question is, can you give me another instance where you could see that this would result in a curve which is not strictly monotonically increasing in terms of intensity distributions?
Sir, if the original image has intensity distribution over the entire range of the intensity spectrum, then the transformation will be a strictly monotonically increasing.
Right. So the moment, suppose I have, for example, I1, there is some 100 intensity, then next intensity is at, well, let's say only 105. Then what would happen for mapping of 101, 102, 103, 104? To what values do they get mapped to? There is a value 100. After that, in my histogram, next value that I have is 105 only. Now, can you tell me in terms of, you know, where 100 is getting mapped to, you know, where 105 is getting mapped to. Now, can you tell me where 101 to 104 will get mapped to? Am I clear, or I would just draw something and then show you if this is not clear?
Same as 101.
Yeah, maybe I'll draw something to make it clear. See, I have a R of S. Okay, this is my R. What is the y-axis here? What should be this y-axis? PR of R. Okay. Now assume that I have at 100 some value is there. The next value I have 101, 102, 103, 104 at 105 only. Now I know to which S it is getting mapped to. Let me call it as S1. I know where this is getting mapped to, S2. Now, can you tell me where 101 to 104 will get mapped to? What would be the values of S for R equal to 101 to 104?
S1, sir.
That's all, S1, because the summation would remain the same. Okay. Hope it is clear to you. Right. So now we arrived at the fact that this is monotonically increasing function. In most of the cases, this is not strictly monotonically increasing, right? Then what is the impact of this? So what is it that we are going to lose or gain with this? What could be the impact of having a function which is not strictly monotonic versus a function which is strictly monotonic?
There won't be any unique values.
Unique values, yeah, be more clear. I'm sure you are answering
There
it.
won't be any unique values.
Unique values for what?
There won't be any unique assignments.
Assignments for what to what?
Like from R1
The
to
inverse won't
S1, R2
exist.
to S2.
We won't have an inverse.
Yes, sir.
That's right. There would see the mapping from R to S is unique. You could say given a R value, it is always uniquely gets mapped to something. But S to R mapping is not going to be unique, right? That's what we have seen in this curve also. See, for example, this is a function which is monotonic, but not strictly monotonic. Given a R, you could always say to which S it maps to. But given an S, you cannot say to what is the inverse. But do we need an inverse as such when you are going for a histogram equalization? Generally not. You are just trying to make the distribution better. That's all. So you are not too much concerned about again getting an inverse of the image. So that way, practically, you are okay with having an image that is resulting in a PR of R, which is not strictly monotonic. Anyway, the cumulative function is making sure that this is a monotonically increasing function. Hope that point is clear to everyone. So if that is clear, maybe let's work out something else. Okay, then let me stop sharing. Okay, so what I will do is, can I share here, for example, a whiteboard? I have not tried whiteboard so far. Let me try how it gives. Okay, so I'll give you an example now. Let's consider a Let me move all my setup a bit so that I can bring it closer. Oops. Is there any undo here usually? Clear is there? Okay, clear all drawings. Okay. Hope it writes now. Yeah. Now assume that I have PR of R is equal to minus 2R plus 2. Okay. And this is, yeah, hope you all have with you pen and paper. If not, please have it with you right now, because we want to solve and see how it goes. 0 less than or equal to S less than or equal to 1. Okay. First of all, is this a probability density function or not? How many of you say, yeah, first, why don't you draw it first? How does it look like? Your R is varying from 0 to 1. After that, anyway, it is 0. What is its value at R equal to 0? This, maybe I will just switch off my, turn off my camera so that I could put this in vertical mode, horizontal mode. Okay.
Yes, sir. It's a PDF, sir.
A PDF. I would like to see somebody saying it as not a PDF. It's a PDF, but I would like to see. Okay. So let's say here I have PR of R here. What is its value at 0? What's the value at 0?
2,
2, correct. And its value at 1?
0.
0. So it's a linear curve. So 2 points are enough for me to draw this, correct? So this would be my PR of R. How can the probability be greater than 2 or greater
So
than
it's
1?
not probability, it's probability density.
Right, very good, very good. Yes, that point has to be very clear, otherwise it looks confusing. Okay, now I give you this. Now what I want you to do is, this is an analytical expression you have got now. Now I would like you to draw for varying value of S here. I would like to see how your PS of S would look like. Okay. Can you try this out now, right now? I would like to see how does PS of S, the probability density function, would look like. Maybe we will go step by step here. So first, can you compute the relationship between R and S? So S is, you are going to transform this value of R, correct? So what's the expression for it? I want to do here histogram equalization. Okay, so I already should be knowing what should be the transformation function here to apply. In other words, the relation between S and R. How are they related? Can you give me express me S in terms of R?
PS of S is equal to PR of R into dr by ds.
That is there, but before that, you tell me how, given R, how do you say S value? What's the expression there?
Summation from
0 to R
Summation.
integration.
Yeah,
integration.
right. We are dealing
0
with
to
the
R.
continuous then. So integration from
0 to R.
0 to R. And what should be there inside?
PR of R.
PR of, will you write R? You are making abuse
No,
of
no, no.
notation.
Omega,
It will
sir.
be over
Yeah,
omega
something, any other thing other than R. PR of omega,
to d omega.
d omega, right. So work it out in the first place and then tell me what is the relation between R and S here.
Minus R square plus 2R.
There are two solutions. So just check whether both of them are valid solutions. If not valid, figure out which is the valid solution. First, I would also want you to draw this out now. Maybe I will ask you what is it that you need to plot here. Let's say I want to vary R here, okay, and would like to see with varying value of R, which could vary from 0 to 1, correct? So anyway, that's why we skipped the multiplication factor here, 0 to 1. I would like to see here, how does S look like?
Sir, what is the number of bits, sir?
Don't
For
worry
bit
about
time.
it. Why do you need that now? You just think that I'm storing only till 1. This is a continuous variable. I am just storing it from 0 to 1 only. It's a continuous one. See, the moment you are using bits, it is going to be a discrete time, correct?
Yes, sir.
So just think of it as treat it as an analytical continuous time function.
Okay.
And tell me now, R equal to what is it? How is it expressed in terms of S? As somebody has said, what would be this equivalent expression would be 0 to R minus 2W. Hope everybody is working out rather than being passive. 2W. So what would that result in? Minus 2R plus S equal to 0. So you figure out what are the two solutions for R, and out of them, which is the valid solution for R. Yes, which is the valid solution? R equal to, anyone worked it out? 1 minus square root of 1 minus S will be the valid solution here. Right, you would get another root which is plus, but then you could see in histogram equalization 0 to 1 should get mapped to 0 to 1 itself. So this has to be the solution. Okay, now from there, can you figure out what is dr by ds? What is the dr by ds value? No, that's a straightforward one. Nah?
1 by 2 root
That's
1 minus S.
That's all. 1 by 2 root of 1 minus S. Okay, right, good. So is that good enough now to compute? How do you compute now PS of S? That is equal to PR of R into absolute value of, what should be there? What should be there here? Absolute.
Sir, dr by ds.
Right, good. dr by ds. Now, how do you work it out? dr by ds, you know, right? 1 by 2 times square root of 1 minus s, right? Now, PR of R, okay. So how do you express this in terms of S? Because this is what we want to see here. For varying value of S, how it is. So you need to express PR of R in terms of S. How do you do that?
Substitute R value.
That's it. PR of R equal to minus 2 times R. R is equal to 1 minus square root of 1 minus S plus 2. Right? This and this gets cancelled. This is equal to 2 times square root of 1 minus S. 1 minus S. Right? PS of S is equal to 1. So you have it varying from 0 to 1, and this value is equal to 1. Of course, this being PDF, the area or integration or the entire thing should be there. Also, you could see this. This is a uniformly distributed. So you have some triangular distribution to uniform distribution. Is it clear? Okay.
Yes.
Okay, good. So yeah, actually I could ask you by varying the so we have taken here cumulative distribution function and have seen the effect, but rather I could have used other function also and could have asked you to calculate how it would look like and other things, right? Fine. So now I would come to the other question I was posing in that video, which is suppose I know what is the distribution to expect. So now I have a specific distribution that I would say, see, essentially we are hoping that an image is having a good enhancement or a good quality, while you have, for example, an equal distribution in the histogram. Now, assume that I know what is the distribution to expect. Then how do you match them? Any thoughts about that? The clue is you could still use histogram equalization.
So is it histograms? Is it histograms matching? Histogram specification?
Well, don't,
Was
yeah,
that
I wanted to say the name a little bit later because that's not going to matter. Tell me how you do it, that's all. Don't tell me the names, you tell me how you achieve it.
will we have two images. We
Hmm.
will first equalize both the
No,
histograms,
I'm not
and
giving you
then
two images. I gave you one image, okay? And the desired histogram for that image. That's all I have given you.
we'll compute the CDF of both the histograms first.
You compute the CDF of,
CDF
okay, right. Hmm. Then,
will match the will find out which value of this CDF, the value in this CDF is mapping to the other value in the CDF.
okay. So I will just pause here. You are partly right. Are we mapping CDFs actually? How are we using CDFs here? Can anyone shed some light on that? Can you right away map the CDFs and say something? You are half the way. You are almost right. But I would like to see, is it directly the CDFs that we are looking at or something else?
So by giving us the desired histogram, you're providing us with PS of S, right?
You are providing a PS of S. Yes, in a way, yes. I would agree. Yes.
So if we have PS of S, we already have the original image. We can get the PR of R. So with this, we get the DR by DS directly.
Uh,
So
wait.
then we can apply
No,
that
no, no.
transformation.
That won't be straightforward. Lot of our assumptions would perhaps fail there. See, you don't know the transformation. What transformation would give you this? You don't know in that case. That I was also thinking in similar lines to start with, but actually that doesn't give you the transformation that maps one to the other. I'm also telling you to make use of the histogram equalization. Okay, and then Sumant is almost there, except that he's mentioning you would look at CDFs to match. Is it directly the CDFs that you are going to use to see where it gets mapped to? Yeah, I think Sumant, probably you mean
No, sir, not exactly.
right. So can you be more precise there? What you would do?
So from CDF, we'll equalize again both
Mhm.
the histograms. Then we can match like the values of this to that.
Yeah, almost there. Can anybody again be more any other? Can you make your own way of presenting that? Telling you he's almost there. I think you also would have got it. You use histogram equalization. That's the basic idea. But how do you, earlier histogram equalization is something that is giving you a equal histogram. But now you know a particular histogram. So how do you make use of histogram equalization now?
So I think we equalize both and then take the inverse something kind of.
Very good. That's right. So you apply histogram equalization on both the histograms. Okay. So now, for example, an intensity I1 in the given image, you will know once it is histogram equalized to what intensity it mapped to, right? So that intensity, now you take the inverse transform from that to your histogram to which you want to map. So you, instead of assigning that, now take the inverse transform of it and you apply this intensity there. Okay. Do you smell any issue with this taking inverse transform here?
If it's not strictly monotonic, then
Right. That's right. This is the issue that you would face. Other than this, the rest of the things are in place. So what usually done is there is now what would happen essentially, instead of having a single unique inverse, you will know that it could map to any of the a given set of values, correct? So what is typically done one way is that among them, which is the closest to the current intensity, you take that particular mapping. Of course, whatever you could do any other thing also, we will not make much of a difference. For example, you might look at average of all those values and you could assign that, but this is typically what people does. So this is referred to as histogram specification, okay, or histogram mapping also, as Sumant is mentioning. That's all. This is what you do there. Is this concept clear to you? we already now finished histogram specification or histogram mapping. So instead of now assuming that it has a uniform distribution of bars in the histogram, you now have a prior knowledge on how it would look like. Okay, so maybe I have some slide here, let me check. As you could see here, for example, you know that under good lighting conditions, this is something to expect here, right? This is the histogram to expect. And this is what you have. The initial histogram is very bright. There is not much contrast here. You are here. So what you would do, you apply histogram equalization to it. So you would get a better equalized histogram here. To this histogram also, you would apply equalization. Then you know, for example, here a value of 100 is getting mapped to here, let's say to 70. Okay, and now this, in this you take 70 here in this equalized histogram of the second image, and you would see the inverse of it where it is going. Assume that this 70 here is going to somewhere 40 here. So then what will you do? Where you have here 100, to this 100 you will assign 40 here. This is the whole process of histogram specification. This is referred to as, you are specifying a histogram. What is the histogram to expect here? So this is referred to as histogram specification. In images, for example, in anatomies and all, you know, if you have some prior knowledge about what is the distribution to expect, so this is something, then you have the knowledge of this, and this is how you would then use histogram equalization to map this histogram to the other histogram. Again, this mapping, this being in the discrete domain, and because of other reasons also, you won't get a perfect mapping, just like the same issues that you had, because anyway you have two histogram equalizations, right? And then on top of it, another inverse transform also. So the problem is, the earlier problem has been amplified by 3 times here, but still you could get a very good approximation or a very good enhancement to this image than using a simple equalized histogram.
So,
Yes, sir.
so what is the like the difference between this, the second histogram and the first histogram after equalization is
Right.
only in the range of values, right?
Not necessarily. See, the way this gets mapped to, see how, for example, to get a value here, what I would do there, I will sum up from here to here. Okay. For example, I want to get for s equal to, let's say this s is varying from 0 to 255. Okay. Now what I would do, if I want this R, let's call it as R1 and R2. This R2 is varying from, for example, 0 to 255. I want a value at R equal to 10 here, let's say. You see here how it is getting mapped to, there are already a lot of pixels here, correct? So that would in fact get mapped to something farther here than what it gets mapped to here. You remember that formula now? What you do, integration to whichever value, for which value you want to compute, till that extent you integrate it and then multiply it with the maximum value, right? So the same value of R, if R1 equal to R2, both of them would get equalized differently. But again, there is some equalization, so that's why you start from here and go from here to there.
So although the plots, the equalized plots look the same, but the mapping is different for
Yes, that's right. The map, you are, so from two unequal, two different fellows, you arrived at the same platform. Okay, you have come to the consensus. But if you track back how you got this consensus, this gets mapped to a different fellow here. Is that clear?
yeah, okay. Yes.
Good. Any other
Sir?
doubts? Yes.
So in some cases, like histogram equalization is not that good. Like contrast stretching is better than histogram equalization in some cases.
Exactly. See, the
So
very assumption here we are making is we are making that all the bars should be more or less same, and it should have equal distribution, and that is how we are characterizing an image as a good image. But there could be image, see for example, let's say you are taking a photograph with your DSLR camera or something like that, where you want the object to be in focus and the rest will just simply blend, and then it is showing that way, then probably your definition of what is a good image is different there. The object should get clearly seen. But if you now try to look at and interpret it in terms of histogram, then it is not in terms of the histogram being equal, right? That's why so we are making some assumptions on what's a good image is, and this definition itself would vary from, this is a lot of generalization, and this definition would vary from image to image. So this is not, that's why if you go and blindly apply histogram equalization everywhere, this could even worsen your results if that is not applicable to the scenario you have in that particular image. So this is some general guidelines that we are just looking at here, that if this distribution is so and so, this could be good, but there could be a lot of violations to this case. So that's why to say which is the one to always apply, there is not one go-to method which you could always apply. Sometimes a simple contrast stretching would be good, sometimes not doing anything is good, okay, sometimes histogram equalization is good, sometimes histogram specification is good, sometimes histogram specification could be the worst thing to do. For example, in a medical image you are trying to find out if there is any abnormality in a given region, and if you have obtained this histogram based on an image which is normal and then trying to match them, probably you would be making the detection of the abnormality more difficult. So that's why you have to be very very keen, and you have to be very critical in figuring out which is the best one to apply for. Does that answer your question?
Yeah, yes, sir. Like my question was,
Okay.
like the cases where histogram equalization is like not a good option. Instead, contrast stretching is a good option.
That could,
So
yeah.
can we extend that concept in this histogram specification? Like I mean, instead of equalizing the histogram, we'll do contrast stretching for both the images. So
But
can we
where do you get
extend
in,
to?
no, can you, how can you get in every instance, it's in very rare cases you have the histogram to which you want to map it to. You don't have this information all the time. In very limited special cases you have this information. So when you have nothing, the best thing you could do is to assume that your histogram is more or less equally distributed.
Okay, yes, sir.
Does that answering your question?
Yeah,
Still?
yes, sir.
Okay, good. See, very rare cases. It's also, for example, when you are doing some study of a very similar population, you already know it, and now for some reasons this image got screwed up, then only you could use histogram equalization. That prior knowledge, having that, you will have it in very limited instances.
Yes, sir.
Yeah.
Sir,
Yes.
sir, for the inverse to work out in histogram specification, shouldn't the transfer function be strictly monotonous?
Yeah, ideally it would be good to have it, but that's unfortunately not in our control. What is it that is what you dictating how, whether it is monotonically increasing or strictly monotonically increasing? What is it that is dictating this for histogram equalization? I think we asked a very similar question in the beginning, and yeah, some of you are answering this. What is it that is dictating whether we get a strictly monotonous function? Ideal is to have a strictly monotonically increasing function there, right, as a transformation function. But what is it that is dictating whether we get it or not?
The
Based
initial
on the initial
histogram.
histogram of the image.
That's right, based on the initial histogram, and then the approximations to the integer. These are the two things that are affecting whether we get a monotonically increasing, whether our monotonically increasing function is strictly increasing or not, right? So that is unfortunately out of our control, because that histogram is given, so to that which you want to map, and then the transform function is also is fixed. It's a cumulative function you are using for finding out the mapping. You are using it, but it's not the final one is not CDF. That distinction has to be clear. Otherwise, this won't be anymore. That is where the mistake was in my previous class when I was saying PDF of a CDF is still PDF. That's a very wrong statement, because you are not taking this PDF as a CDF of it. This is, you are using CDF to just find out the mapping, and then you are moving the whole bar to the other place. So that's where the flaw is in the logic I was mentioning in the last class.
How do I find the inverse mapping?
That's what I was telling. See, suppose in the earlier one, assume that an intensity of 10, okay? You do not know the unique mapping, but you still know to what set of values it gets mapped to. Assume that there is an intensity 10 here that is getting mapped to, let's say, there 9, 10, 11, 12, okay? Or assume that 10 is there, that is getting mapped to 12, 13, 14, 15. Then what you do is, an approximation is you take the nearby one. This is commonly done. So if you have their set of 12, 13, 14, it could map to any of them. You simply take 12 and map the both. Because the whole thing is an approximation, this is yet another approximation. You do it because there is no other way. Any other doubts here as far as histogram specification is concerned?
So, like instead of taking the equalization part, like Sumant said, we can do also stretching in this regard.
You can do this.
So, like, how is it different? Like, how is stretching different than equalization?
Yeah. Can anyone again try to answer this question? How is stretching different from histogram equalization?
So stretching is for only some portion. Like, I mean, if the histogram, like the actual histogram of the image is from 85 to 150.
No, maybe in terms of intensities, can you tell me the key difference between stretching and histogram equalization?
So we are not focusing on the amplitude in contrast stretching.
Yeah, that is there. That is fine. But in terms of the final result, what is the difference between histogram equalization and stretching?
The intensity values will be more or less same in equalization, but in contrast stretching, the intensity's values will not be not uniform.
Yeah, maybe you might mean the same probably, but let me say it and then you could comment on that. See, your bars would remain same. If you plot the histogram before and after contrast stretching, your bars are same, except that their placement is varying. And their placement is purely dependent on the intensity value and not on the number of pixels having that intensity and number of pixels before that intensity. That is not there in the contrast stretching. On the contrary, in the histogram equalization, the bars will not need not remain same. As you have seen, for example, multiple intensities would get mapped now to a single intensity. That means all these small bars will add up there and give you a big bar there, where earlier there is only one bar. So the number of peaks that you have could reduce in case of histogram equalization. That's one thing if you see it in terms of output intensities. Another difference is now the what is the new intensity that you are assigning in case of histogram equalization is not just dependent on the magnitude of that intensity, but the percentage of pixels that are having that particular intensity plus intensities before that. So that cumulative effect is something you are looking into, and then you are deciding where this intensity should go. These are the two key differences that I see here. Is that point clear?
Yes, sir. So another thing I wanted to ask, like, is the transfer function for this histogram stretching, is it strictly monotonic in this term, or is it just monotonic?
See, all you are doing in case of, see, there is no transfer function. What all you are doing is, you are simply the placement of these bars you are changing when it comes to contrast stretching. Nothing else you are doing. All you are doing is the minimum whichever is there, you are bringing that to 0. Maximum which is there, if it is an 8-bit, you are taking it to 255. In between, how close it is to 0 or to 255, accordingly you are placing these bars. and thereby ensuring that you have the distribution of intensities, but not worrying really about how many pixels are having that intensity.
Okay, sir.
So in that case, if you want to draw that function, it would be strictly monotonically increasing function. Will that not be the case?
Yes, so since no two bars can be placed at the same position.
That's right. That's right. So there is no two values are corresponding to the same intensity here. You are not merging the intensities. So that's a strictly monotonically increasing function. It is like we have seen the class earlier, like piecewise linear. Okay, this is instead of piecewise linear, this is a linear function essentially. That the equation itself tells you that's a linear transformation, right? You have R here, you have S here. So you are simply drawing this curve depending on where the starting point is. This would be at 0. The starting point would now go to, at that pixel it goes to 0. Maximum would go to 255. That's all you are drawing there. So maybe we could draw it again here. So you had there, for example, this is your new value you are assigning, or your initial values are, okay, the original image, S the new ones. Assume that your, in both cases, this is, let's say 255 or L-1, whatever you want to say, 255 here. Assume that you have this I min and I max, okay, I naught and I1, let me call it. Now what would happen? This would be mapped to 0, and by the time I1 comes, this would be mapped to 255. That is all the transformation is. So this is monotonically increasing transformation function. Okay. So yeah, I think we will stop here for this part, and then there are some questions I think a few students have about the submission of the second assignment. We could discuss it